pure or the basic aspects of trying to understand the structures, trying to utilize the fabrication methods, and then lastly comes is how you are going to understand the properties. What is fabricated? You need to understand how this material is formed. So accordingly, this material characteristics, the response to the simulations, like mostly if I am talking about computer simulations, or like if I am talking about external stimulus, let's say like mechanical, electrical, thermal, magnetic, optical. So how these all aspects are going to affect the properties of my material. This becomes one of the biggest aspects of my study, and we want to understand the relations between these materials and its properties. Lastly, all these are connected to each other. So one important point is, when I know all these structures, I understand the performance now. So what particular performance I am expecting from these materials is becomes a very important thing for me now. So lastly, like when we know all these four pillars of this research, wherein we can understand pure state art, we try to understand the structures of these materials, we try to know the processing of these materials, we try to understand the performance of these materials and then properties of these materials. So what remains is how we are going to scale down now, or how we are going to scale up the materials. So already we all are working in bulks, we know everything in bulks. Slowly the technology requires or the requirement of this technology is how we are going to microscopically make these materials. Almost like now for decades we are trying to move into the length scales of nanometer scales. So here you can see that this length to 100 nanometers we are moving. So why we are is the importance that we are trying to miniaturize all the devices. Earlier, like if you see, our computer is almost a room dimensions, but now a computer is very small on your hand, palm hands, you can see. So Samsung here has developed a small computer which is almost almost like dimensions of your mobile. So these computers are now miniaturized. So that's why the length scale is been changing to nanometer scales. And now the atoms, nanoclusters, nanostructures are becoming more important to study. So accordingly, like we need to understand now this, like how this nanometer like synthesis can be done or fabrications can be done. Two are the important aspects. The second one is the bottom-up approach. So if I try to see a bulk, and now I try to break down this bulk into small pieces, like these small shape squares I have shown. So what I can go is, I can cut down this bulk slowly in parts, and I can come to so accordingly from top to bottom I can go and make certain kinds of nanostructures, particles, nanoneedles, or nano dimensions. If I atom, so one atom connected to another atom, and so one atom is connecting to the other, the third. And this question is very important. So is another question comes in mind, is it surfaces or interfaces? And the answer is yes. What actually we are trying to do is, or what we are actually trying to, so where it's simply defined as we already have studied in our BScs, like how the cohesive and adhesive forces are taking place when you have a surface and interface. So you can surfaces are affecting the surface tensions or the contact angles. So you can see that if I have the polar molecules present on my surface, then I can see that these polar molecules can get attached with the molecules by adhesive forces, and accordingly, if there is a strong bonding taking place, then this means that there will be a very good contact angle, or the wettability will be more higher. So accordingly, one can actually tune the surface properties, understanding the surface tension on the surfaces and the interfaces. So if I want a high energy, or if I want a high or a low surface energy, so that means I can use some treatments, like if I use a plasma treatment or a chemical etching treatment, I can change the low surface energy to high surface energy. Or if I can use an adsorption or hydrogenation processes, so if you can see, like if I use a hydrogenation here, then the H2 will be formed, and then these bondings will be more higher. So I can make my surface go from higher surface to lower surface. So here you can see that this pyramid shows you like the greater the portion of your polar groups, higher will be the attractive forces, higher will be the surface tension, and high will be the contact angles. So therefore, this is very important. You can actually see that if you put an oil or if you put an water on the surface, you actually can see what is going to happen. So this means that the chemical composition at the surface is much dependent on the surface energy. Secondly, these polar groups, if not properly polished or they are unpolished, then they causes high surface energies. You can see that most of the contact angles can be leading to different kinds of surface understanding or properties. So not only that, your temperature and surface roughness can be one of the effective points to understand. So I have made just shown you small table which shows like how the wettability of the surface can change, and how the hydrophilic and hydrophobic surfaces can be made to achieve different kinds of applications. So coming back to understanding the properties, that not only this simple tool to understand the surface properties, but there are more sophisticated techniques like X-ray diffractions. You have surface X-ray, surface or glancing angles X-ray diffractions. You have XPS, you have XES, which shows the electronic properties or the chemical composition properties. You have XFs, you have polarization dependent and reflection absorption spectroscopies. You have Raman spectroscopies, you have AFMs to understand different kinds of properties of these surfaces and interfaces. So let me come to application part of this. Now you can see when I'm talking about nanomaterials and I'm talking about the surface and interface. So we already know this. This is a well-known mechanism now. Everyone has came across this mechanism. So you can see at the surface and at the interface now. The interface is between the two grain boundaries now, and at the surface you have polar bonds. So what happens is now when there is no interaction of any gas on the surfaces, what I can see is the current and voltage have very linear relationships. Now when I'm talking about a linear relationships, that means I'm making a contact which is ohmic in nature of this study. Now when or as soon as I input some reducing gas on this surface, what is going to happen is this H2 will react with the surface is polar bonds of O minus, which is chemi-absorbed oxygens present on the surface. And what happens is there will be a reaction taking place at the surface and interface. So electrons will be given in, and these electrons can be passed through the interface grain boundaries because the grain boundaries will be lower down. As a result, I can see that the current will increase and therefore the resistance will be lowering down. So if you see that the potential barrier here now goes down and electrons can be easily conducting. On the other hand, if you see for an oxidizing gas, the polar surface is, in this case now the oxidation gas will react with the oxygen to make an O2O minus, and electron will be removed from the surface. Thereby the grain boundaries will start to grow up. Now at the interface, an electron on barrier is taking place, and electron will not move very easily through this. Therefore this barrier will increase and you can see that the current will be lower. So now what I want to tell you from this application is that how this surface is important, because this surface and interface are very important for me. So if I know how can I control this surface and interface, that means I'm going to control the exact output of my device. Is coming down to various applications. Now energy being a very important part in our life now, because we are moving on to understanding the renewable energies and battery is one of the very important field, or you can say that electrochemical devices are playing a very important role in energy aspects, wherein battery, supercapacitors, or solar water hydrogen splitting is playing a very important role. You can see here I have shown a very simple cartoon here now. Now you can see these are the two electrodes which is at a potential, positive potential, and the other one is at negative potentials. And we have grown some layers on these electrodes. What you can see that the contour of the surface is defining the contact angle now. So you can see the contact angle will be defined by the contours of the surface. Not only that, at the surface and the electrolyte, what you can see is there is a capacitive double layer, Helmholtz layer, and this will be governed by again the contact angle on the surface here. So the important point is like how I'm going to control this surface will affect my total current and potentials of the device applications. So here you can see that if the surface and interfaces in electrodes are and the electrolyte are porous in nature, what is going to happen is there will be a high intercalation taking place between the electrolyte and the surface as electrode. So this means that there will be a possibility of very high redox reactions taking place on this surface, and accordingly you can see that if you have a porous layer, then that means your current will be pushed here, so that your ore potentials will be lower and you can have a very high currents and produced at a very small potentials, applied potentials. So this means like this application of understanding the surfaces and interfaces plays a very crucial role now. Now I'll just try to sum up my talk by giving a simple example. This is our current paper which was published, and what we have done is we have taken an antimony selenide. Now antimony selenide has an intrinsic bonding, so along this it has a covalent bonding, and along the horizontal face it has a van der Waals bonding. So what it shows me is that along the covalent bonding I can see that there are adhesive forces taking place and the contact angle is becoming lower. So I am getting in an hydrophilic surface if I am stacking in the antimony selenide along the 0 Ka0 planes. On the other hand, if I'm trying to make the antimony selenide in such a way that I'm having H0L planes or H00 planes, so what I'm doing is I'm actually at the surfaces I'm using van der Waals interactions, and now these interactions make the water contact angle much higher, and therefore I have an hydrophobic surface now. So why I want this surface is to make a bifunctional filter now. Now this filter will be very essential for me, such that if I use this filters on a mesh part. So here is a mesh, and we have grown this is antimony selenide oriented surfaces. So what you can see is that when you put oil and water on this surface, what happens is now it is having in hydrophobicity for the hydrophobicity towards the water. So on the surface the water will remain while oil will penetrate. So this means like you can have a filter now, and now this filter is going to be used in such a way that oil will be separated from your water. Now if I have uncontaminated air water, so what I will do is I will use this surface now. So what I will do is I will irradiate this surface with some light so that electron holes are generated, and now if the contaminated water is present, like dyes are present in this, then I can degrade the dye at the same time. So these are bifunctional materials we have been developed, and you can see that this is our device where you can see that for just understanding we have put some colors into it. So this is a methylene orange and this is hexane which was mixed together. And then when we put into this device, what we see is the methylene on orange, which is having a water part, it remains at upside, while the hexane, which is having an oil part, goes through it. So that means we have a very good filter now. And now when we put in light and put some electrode into this, what we can see is we can degrade this. Now this electrode is nothing but our mesh structure here. So that means that the surface is very important, and how you control this surface, you can control the bifunctional properties wherein we have shown in antimony selenide that we can use this simple material for making such filters. Likewise, I would like to sum up this talk that at length scales of nanometers, you can see that at the surface and interface, they are going to play a major role defining overall physical properties. not only the physical, but I will say that physicochemical properties will be governed by the interactions at the surfaces now. And now, almost like we are going to miniaturize all the devices, so that means surface and interfaces will become an important part of our study. So using various techniques, we can identify and study these surfaces and interfaces. And what remains a challenge for all our scientists is that how we are going to actually control the surface and interfaces. So this is the main focus of the study currently going on worldwide, and I feel that this becomes a very important aspect for all the researchers today to study the surfaces and interfaces and try to make various devices which are commercialized. So lastly, with this, let me make different and beautiful surfaces and interfaces. You can see that we can make a lot of surfaces and interfaces. So our facial itself is a very good research topic to study. And with this, I thank all the organizers for giving me this opportunity to talk. I hope and congratulate them for a successful conference. Thank you very much. And I would be happy to have some questions now.
Thank you, sir. Thank you very much. As relevant to the topic, what makes nanomaterial